Hello, my name is Michael Kaler, and I am the lab manager of the GIME Diffraction facility, located at the University of Tennessee, Knoxville. This video will show you how to perform a gonio experiment using the XYZ stage. This is the more detailed training video explaining each step. I also have a shorter video linked above that covers only the basics for those who have already been trained but need a reminder on how to perform the measurements. Here we see the Empyrean system set up with the XYZ stage. A lot of this will look familiar to those of you who have watched our tutorial video on how to perform powder diffraction. For this configuration, we still have the Solar slits, programmable divergent slit, the mask, and the anti-scatter slit on the incident beam side. On the diffracted beam side, we have the programmable anti-scatter slit, or pass. We have the large Solar slit. We have the nickel filter, and we have the pixel detector. When aligning our sample, we are going to be shooting X-rays directly from the source into the detector. That means that a large intensity is going to strike the detector. In order to absorb some of those X-rays, we will use an attenuator. This one is a copper 0.1. If we want to install the attenuator, we want to align it like this, and then place it just to the left of the Solar slit. It just goes all the way in and sits there pretty loosely. Also, for alignment purposes, we want to use the smallest divergent slit possible, which is 1/32. Remember that the anti-scatter slit should be 2 times whatever the divergent slit is. So this needs to be 1/16 of a degree. I believe right now I have half of a degree in there, so I will change that out for the 1/16. Remember, just push all the way in and pull back until it clicks. And those are all of the changes for the incident beam side. For the diffracted beam side and for alignment, we want the programmable anti-scatter slit to be as open as possible, so we will use the computer to set it to be 4 degrees. The recommendation I received from Panalytical is to remove the large Solar slit on the diffracted beam side. Honestly, I have tried it both ways, with and without the Solar slit, and I don't really see any difference. You should see somewhere on your screen right now a comparison of 2 patterns that I collected with and without these Solar slits. Officially, you should probably remove it, but I'm just going to leave them in there as that is one less thing I have to worry about remembering to put back in. Other than that, there isn't really anything physically that you need to change on the diffracted beam side. Once we have changed the optics in the sample chamber, we want to go to the computer and open data collector, seen here and down here. I will left click, enter your username and password. We now want to connect the computer to the instrument, so we will choose Instrument, Connect. Your options might look different from these. Here in the diffraction facility, we have the option of the XY platform with Z adjustment. You also can choose your beam path, but for powder diffraction, we typically want to make sure the beam path is 1. I will left click OK. This window doesn't really matter all that much if you only see yellow triangles. If you see red X's, that's a bad thing, and you will likely want to contact Malvern Panalytical about that, but I just see yellow triangles, so I will choose OK. This window tells me that someone saved offsets previously. You can see here that it asks, do you want to apply these offsets to the diffractometer? And clicking no will clear them. We will go ahead and clear them because we will create our own offsets. I will choose no. We might get another window that pops up that asks you a similar question. If you do, just choose no. The first thing that I like to do before I forget is to align the sample in X and Y. X is left to right in the sample chamber, Y is front to back, and Z is up and down. In the Gyme diffraction facility, we have an alignment camera placed above the sample. In order to access that, we go to Tools and choose Alignment Camera. Let me make this a little bit bigger and left-click Start. Here we see our sample. The crosshairs show you where the center of the X-ray beam is. I'm a little off-center. You can see that I am currently at the 0, 0 position. If I right-click, I can choose Move Stage to this position, and now you will see the sample shift. Now it is better centered. Another nice feature of the camera is this image coordinates right here. You can see that as I move my cursor, those values change. If I place it close to the center of the crosshairs, that's about 0 and 0. I can use this to make sure that my sample is centered and also measure my sample. For this sample, I just want to perform phase identification, so I don't really care if the beam falls off of my sample, so this is good enough for me. I will left-click Stop, and then I will close this window. Here we see 3 tabs: Instrument Settings, Incident Beam Optics, and Diffracted Beam Optics. This first tab, you may or may not even need to do anything with this. What I am going to show you here in this video is how to perform alignments using a batch program that carries out all of these steps for you. I have created another video that shows you how to make this batch program, and if you would like to view that, just click the link that should be appearing at the top right of your screen. Now let's come over here to Incident Beam Optics. I will double click. I get this window. In here, we can tell the computer what hardware we have installed for the Incident Beam Optics. I will go through each of these tabs one by one. The prefix module is the programmable divergent slit. That's good. For alignment, the divergent slit should be 1/32. The anti-scatter slit should be 2 times what the divergent slit is, and if you recall from earlier in this video, we changed it to be 1/16. I have a 10mm mask installed, so that's fine. You don't need to change the distance to sample. You'll notice that when I click the top row, it becomes the bottom row. Beam knife, I'm not using one, so that's none. Solar slit, I have the 04 radian. I have a filter, but it is on the diffracted beam side, so for this side, it is none. If you recall, we installed the beam attenuator earlier, so I will left click and choose the copper point 1. Then I will choose Do Not Switch for Usage and Activated. Mirror, that's also none. I will left click OK. This window just tells me to make the physical changes in the system that I said I did in these tabs. I changed this so I can left click OK. Because it is so important that you insert the beam attenuator, it is reminding me to do that in a separate window. As long as you have done this, you can go ahead and click OK, but make sure you put the attenuator in. I can't stress that enough. Let's go to Diffracted Beam Optics and double click. The prefix module, there we have our detector and the programmable anti-scatter slit or pass, so that's good. For alignment, we want our anti-scatter slit to be as large as possible, so I will choose 4 degrees. We don't have a receiving slit. We have the nickel filter that gets rid of the beta radiation. On this side, we don't have a beam attenuator. For the detector, these are the settings we use for measuring your sample, but for alignment, we want to change this to receiving slit 0D. I will highlight this and change it to 0.1 and hit tab on the keyboard. We see that it becomes 0.165 and changes to 3 active channels. Collimator, none. Solar slit is the large 04, and mask is none. I will click OK. wait for the changes to be made and the window to close. And now, just a personal preference, I like to left-click instrument settings so that I can watch these values change. I will go to Measure, Program. Here I have the file that I want to run. You see that it is a general batch. If you need to, you can click Browse and find your program wherever it is on your computer. This is the one that I want to use though, so I will open it. Here we see that I am not saving any of these scans. I don't have to worry about file name settings or anything. I will just click OK. Let me reposition these a little bit. You don't have to worry about this part. At first, the system will make sure that all of the offsets are cleared, that the tension and current are the right settings. It will then set your angles and Z to 0. And now it will begin a 2 theta alignment. 2 theta just means that the detector is moving a little bit and we are trying to find where the source is shooting directly into the detector. Ideally, that should be perfectly at 0, but it is usually a little off. Here we see that the software determined that it is 0.0002 degrees off. We will save that here in a little bit as our new offset to make this our new true 0 position. Next, we are aligning along Z. Z starts out very low and then starts moving up. Once it is too low, we get maximum intensity because the beam is shooting directly into the detector. But once your sample gets high enough, you see it drop down in intensity. That pink line is the plot of the first derivative, and the software will find the maximum point and then move Z to match up with that to make sure that your sample is in the center of the X-ray beam. Next, we are testing omega, and omega scans just make sure that the X-ray beam is parallel with the top of your sample. If your sample has a little bit of a tilt to it, this will account for that. We see here in omega that it was a little off, not too bad, about 0.03 degrees. Now omega and Z are coupled, so when one changes, the other one typically changes. What this program will do is go back and forth and measure Z and omega a total of 3 or 4 times. In my experience, that is usually enough to make the two values stabilize. You might want to test yours out just to make sure this is enough for you though. For now, we will just wait for the alignment to finish. I will speed this video up a little bit to save some time. At the end, the software will set whatever values of 2 theta and omega that it has determined to be the new 0 positions as offsets. I didn't set it up to save X, Y, and Z as offsets, so you will still see them there under instrument settings. That's a personal preference. If you would rather save them as offsets, you can if you like, but I like to keep those as they are so that I can see them on the screen. Now we see that no program is executing, and we see that our angles are all 0, and if we go to user settings and fine calibration offsets, we will see that we now have some offsets. These are the values of 2 theta and omega that the batch file determined were best for our sample. Whenever you put a new sample in the chamber using the XYZ stage, you will want to perform these steps in order to align it. So I will click OK. We will now go back to the chamber and switch our optics to our measurement optics. We need to remove the attenuator. If you forget to do that, you will most likely get no signal when you try to collect your data. We will also change back the anti-scatter slit to whatever we want to use for our measurements. I'm going to use a 1/4 degree divergence slit, so I will change the anti-scatter slit to 1/2. And that is all we need to change manually on the incident beam side. On the diffracted beam side, nothing needs to be manually changed unless you removed the Solar slit for alignment. If you did that, reinsert it before making your measurements. Now that the optics have been changed, let's announce the changes in the computer. Incident beam optics, I will double click. I still like to go through every tab even if I didn't change anything for that tab, just to make sure I don't forget something. For divergence slit, I'm going to use 1/4 of a degree. If you use something different, then change it to whatever you want. My anti-scatter slit is then 1/2. Mask, that's still 10 millimeters. I still don't have a beam knife. Solar slit didn't change. Filter didn't change. I removed the beam attenuator, so I need to change this to none. And the mirror didn't change. I will click OK. I did these things, so I will click OK. For diffracted beam optics, I didn't manually change anything. Maybe you removed and reinserted the solar slits. But even if you didn't do that, you still need to come here and make a couple of changes. Prefix module is still pass. Anti-scatter slit should now equal your divergence slit, so for me that's 1/4. Still no receiving slit. I still have the filter in there. No beam attenuator. For detector, I want to change this back to scanning line detector 1D, and it should automatically fill in this number and give you 255 channels. Collimator none. Solar slits, here I'm just going to leave this. If you removed it for alignment and chose none for the alignment step, then you will want to change it back to either 02 or 04, whichever one you were using. I'm choosing the 04, and mask is still none. I will click OK. Now that all of our optics and tabs are set up correctly, I am ready to either make a program or measure a program to collect my data. Most of the time, people don't make new programs once they already have one made. They just open old ones, modify them, and resave. Let me point out here that if you have programs that you made using another stage, such as the reflection transmission spinner stage, they don't work for the XYZ stage. In that case, if you don't have any XYZ programs made, you may want to come here, choose New Program or File, New Program. You will want to choose an absolute scan. OK. Let's close that to give a better look. Here we see the configuration is the XYZ. We are on beam path 1. Scan axis is gonyo, which is what we want for this type of experiment. Let me come in here to settings. This is largely optional. You don't have to set up settings here, but the nice thing about doing this is that if you set these settings to match the settings you put into the incident beam optics and diffracted beam optics, once you run this program, it will check these settings versus these settings to make sure they match. In this way, if you make a mistake, it will catch it and warn you so that you can correct that mistake. If you don't want to do that, I would still recommend that you come down here to detector and change that to pixel and make sure that it is on scanning line detector 1D and has 255 channels. So if you don't make any other changes, at least make that change. I will quickly go through and set up the settings here to match what I did over here. For my incident beam path, the prefix module is the programmable divergence slit. I want that to be 1/4 of a degree. For the incident beam, I don't have a filter. My solar slit is the 04. I'm not using any beam attenuator for the measurement. I am using the 10mm mask. My anti-scatter slit should be 1/2. I'm not using a beam knife. Whoops, my mistake. I meant to choose none. And I'm not using a mirror. Just as a word of warning, if you have a roller ball on your mouse, then I recommend that you don't use it. You'll see here that if I use it, it simply rotates through the options here rather than scrolling down. Let me change that back to none. I will scroll down by left-clicking here, and now I will fill out the diffracted beam path. The prefix module is pass. Fas is for our in situ high temperature measurements. I want pass. I want that to equal my divergence slit, so that is 1/4. The filter is the nickel for the beta radiation. Solar slit is the large 04. My detector is good. I set that a few minutes ago. Beam attenuator, none. Collimator, none. Mask, none. And receiving slit, none. Once that is all filled out, I can click OK. At this point, you can choose your starting angle and ending angle. If you don't know what to choose, I would recommend 5 or 10 degrees for your start angle. End angle, if you are just doing phase ID, 90 degrees should be fine. Step size, again, this is very sample dependent. If I'm not sure what to do for step size, I will start with 0.026, and if I hit tab or click, you'll see that it changes. For the pixel detector, you only have certain step sizes that you can choose, such as 0.006, 0.013, 0.026, and so on. If I forget any of these numbers, I can just enter some number close to what I want it to be, click away, and it will change it to the closest option. My time per step I see is 5 seconds. That will give me an experiment time that is approximately 1 minute. If I'm not entirely sure what my pattern is going to look like, I like to set up a 9 to 11 minute experiment. So I will do 50 seconds. I see that is an 11-minute experiment time, so that sounds good to me. At the end of 11 minutes, I can look at the data and decide if I need to change any of these parameters to improve my results. Once all of that is set up, I will go to File, Save As. Again, you can click around and find where you want to save things. For now, I'm just going to go to YouTube, save it in Programs, and here you see that I have a program set up pretty similarly. It was 10 to 90 degrees. I like to name it with what stage I'm using, which is the XYZ stage. It has the programmable divergence slit on the incident side. It has the programmable anti-scatter slit on the diffracted side. This program that I just made is 5 to 90 degrees using a 0.026 degree step size. I think I did 50 seconds. Yep. And it is 11 minutes long. This way I know what is in my program without having to open it. I will choose Save. Once I have a program ready, I will just go to Measure, Program. Let me navigate to my YouTube folder, Programs, and this is the one I want. Nope, XYZ stage. It should be this one. I will double click. I will click the folder icon here to choose where I want to save it. I'll put it in my data folder, and I'll just name this YouTube example. You can name it whatever you like. Click Save, and then OK. I will close this. Let me take this opportunity to ask you to please like, comment, subscribe to our channel. Anything that you can do really helps us out. It encourages YouTube to show our videos to more people who can benefit from them. If you have any questions, please leave them in the comment section below. Otherwise, thank you for watching, and I hope you have a great day.